The Hybrido technology has been developed for the creation of mid- and large-scale fluid simulations. In contrast to RealFlow's standard fluids, Hybrido is based on a grid of volume elements. The solver calculates the interactions between adjacent cells to represent the fluid's behavior. The particles that can be seen in Hybrido simulations are actually just markers to visualize the fluid's body and velocity. The result of a grid fluid simulation can be seen as the core fluid lacking from details like small splashes or foam. These secondary elements must be created in separate parsers with specific particle emitters. The combination of grid fluid and standard emitters also explains the name of this technology. It is a hybrid method of two completely different approaches. Grid fluid simulations require a specific workflow based on domains and exclusive links. A domain can be seen as an empty container where the fluid simulation takes place. Grid fluids cannot leave the domain, and the simulation's quality is mainly determined by the domain's resolution parameter. To finally create a fluid, an emitter is needed. Grid fluid emitters always consist of two elements, the emitter node itself and an object to specify the fluid's volume. The emitter node is used to define the direction of emission. This direction is indicated by an arrowhead at the emitter's viewpoint symbol. The emitter object can be of any shape, but it must be linked to the emitter node in order to make it work. The last element is a gravity daemon. Without any external forces, the fluid cannot move and will just stay inside the emitter object. These four elements are already enough to describe a complete Hybrido scene. You can move the emitter object to any place inside the grid fluid domain, change emission direction, or create a constant fluid stream inside of a specified volume. Once you are happy with your setup, click on Simulate. After a few moments, the emitter object is filled with the marker particles. When you have a closer look at the fluid, you can see jagged edges. These edges represent the domain's cells. To reduce this effect, the domain's resolution must be increased. So far, we have a pure grid fluid simulation, and here it is not actually necessary to create exclusive links. But this changes completely when you start to add standard emitters for secondary elements, for example, like splashes. Let's have a closer look at the workflow. In the following scene, we will create a rocky coast with a turbulent ocean, splashes and foam. Finally, a mesh will be calculated from the grid fluid. We start again with a grid fluid domain. Now the rocks are added. They have been created with a 3D program and exported to RealFlow's SD format. With the import command, they can be loaded to the scene. For a better handling, they are grouped. The group is called rocks, and now all actions on these rocks can be performed on the group instead of the individual nodes. Then change the raster mode option to static. This action will help to save the simulation time because dynamic and static objects are treated differently. To resize the domain, you can either use the R key or use the node panel's scale settings for an exact result. In this case, the domain is 25 by 10 by 10 meters. The emitter object is just a scaled cube. The cube creates a collapsing pile of water, but please do not make the object too large because otherwise the splashes would look unnaturally strong. To make everything work, a grid fluid emitter is needed. The emitter object is attached to the emitter. For more turbulence and splashes, initial speed is set to 1.0. Jittering creates some randomness and is a more realistic fluid, and we use a high value here. A gravity daemon is also needed. To add more turbulence, we also introduce a noise field daemon. In the next steps, all nodes must be removed from the global links panel. The interactions between the scene's nodes should only be established with exclusive links. We take the grid fluid domain and drag it to exclusive links. All the other nodes from the scene must be grouped under the domain. For the rocks, it is enough to use the group instead of the individual nodes. Now all nodes are linked to grid fluid domain. The emitter object is an exception because it does not contribute to the simulation. A simulation with default parameters gives us a good overview. It is clearly visible that a higher resolution is required. A value of 1 million should be enough here, but it is, of course, possible to use much higher settings. The particle sampling value tells you how many marker particles will be used per domain cell. In this case, there will be 2 times 2 times 2 equals 8 particles. This value is mainly responsible for the creation of splashes, not for the fluid's quality. The quality is determined by the resolution value. The surface parameters are of particular importance, but they will be adjusted in a separate pass. For the core fluid simulation, the parameters of the calculate family can be set to never. If the splashes turn out too high or too strong, then the emitter object should be downscaled to derive motion energy from the collapsing fluid column. When you are satisfied with the results, save the scene. The adjustment of the core fluid surface is a very important step because the surface is responsible for the creation of splashes and foam. The surface can either be extracted from the core fluid's particles or the surrounding distance field. In this tutorial, the field option is used because it is faster but not as accurate as the particle-based method. You also have to decide whether you want to trigger the creation of splash particles with a detail threshold value or not. This value represents the sensitivity of this process. A value of 1 detects any area where splashes occur. 0 deactivates this feature, and the splashes can be created with the splash emitter's own threshold parameters, for example, from the surface's curvature. Here, the default value of 0.2 will be used. Before the surface and its associated fields can be finally created, the calculate parameters should be set to always. The onRequest method should only be used if you want to create core fluid splashes and foam within a single pass. Finally, the domain's simulation parameter must be set to cache because we do not want to resimulate the entire core fluid pass. After the completion of the surface, a grid mesh is used to visualize it. The grid mesh is a representation of the surface and field data of the previous pass. To add a mesh, choose the Grid Mesh node from the Mesh menu. If there is only one grid fluid domain in your scene, it will be automatically attached to this mesh node. The mesh node itself provides just a few parameters because most of the settings have been made in the domain's surface panel. So, whenever you change one of the surface parameters, you have to recalculate the surface and create a new mesh to evaluate it. If you do not recalculate the surface and the fields, the splash and foam particles will not be moved and placed correctly. In other words, the surface can be seen as the connection between the core fluid and secondary elements. You should play with the settings to get a feeling for how they work and influence the surface. You can trigger the mesh creation for single frame directly with the Build Grid Meshes button of the Grid Fluid domain. Once you are happy with the mesh's level of detail and the look of the surface, you can create the entire range of meshes with the Build Mesh button from the icon bar. In the second part, we are going to use standard particle emitters to create splashes. To get more realistic results, the splashes should only occur around the rocks. For this purpose, we will make use of the RealFlow IDOC concept. An IDOC can be seen as a domain that cannot interact with other fluids. On the first look, this seems to be a limitation, but in fact there are many advantages. Simulation speed will decrease because the creation of splashes is limited to certain areas. Independent, non-interacting fluids are faster to simulate. With appropriate licenses, IDOCs can be simulated in a network. You have full control over each IDOC and its associated splash emitter. The results are almost the same as with interacting fluids. Adding IDOCs is a fast process. IDOCs are simply added from the icon bar, and in this case, we choose single. Currently, the IDOC is nothing more than an empty container that can be resized and placed anywhere inside the grid fluid domain. Here we have to place and fit a total of 7 IDOCs, 1 per rock node. Once the eye docs have been placed, grid splash emitters will be attached. This can be done with a single click. Simply choose Splash from eye doc, and RealFlow will automatically add, adjust and attach the appropriate number of splash emitters to the eye docs. The next step is the creation of exclusive links. First, all new nodes must be removed from the Global Links panel. Then the splash emitters and eye docs are grouped and renamed for a faster workflow. Now, drag the splash emitter group onto the grid fluid domain. Additionally, the splash emitter group is added to exclusive links. Then all relevant nodes are thrown into this container to establish the missing connections. Since splash particles can leave their domain, we recommend adding a K-volume daemon. This daemon must be linked to a splash emitter group as well. The daemon's bounding box should be slightly smaller than the grid fluid domain to avoid unwanted particle accumulations at the fluid's borders. Now we have completed setup, and it is time to adjust the splash parameters. This process might require a lot of test simulations to get the desired amount of particles, and sometimes this is a time-consuming task. In most cases, it is enough to adjust a few basic settings. The splash emitters themselves can be adjusted group-wise. Select the group and open the Node Params panel. Emissions rate is certainly one of the most important parameters when you have to control the number of particles, but there are some more settings. One of them is curvature threshold. Small values will create more particles because splashes are not only restricted to areas with a strong curvature. Curvature threshold is very sensitive and time-consuming, so always try to use the highest possible value. On the other hand, it is very easy to create large amounts of particles with this parameter, and in many cases, it is enough to alter only curvature threshold. To keep the splashes together, we recommend small angle variation values. With velocity variation, it is similar, and high variations create more randomness, but this might lead to an unnatural look. Additionally, internal pressure is set to 0.5. Foam strength is an interesting parameter because here you can already control how strong the splash particles will finally contribute to the creation of foam, but normally the default value should lead to satisfying results. Now we can proceed with the splash pass. As mentioned before, the splashes will be created from the previously calculated surface and field data. To use this information for the next passes, the calculate parameters of the surface panel have to be set to use cache. The splash emitter normally requires a certain amount of testing and experience until you have found the working values. The number of particles also strongly depends on the look and behaviour of the underlying grid fluid. Simulation with just a few turbulences will hardly create any splashes at all, even with high settings. So there are scenes where you can just see a few small splashes. In such cases, you should consider increasing the different threshold values or resimulate to get more turbulences. If the number of splash particles is not high enough, you can increase the emitter's resolution and emission rate values. The detection of areas where splashes occur is a very complex process and takes some time, but the iDocs helps to accelerate this process. The final simulation could look like this. The last element we want to add is foam. Foam is created from splashes, and therefore it was necessary to perform the splash simulation in the previous step. The workflow is very similar to the splash simulation, but here we will be using only one common domain instead of one emitter per IDOC. The foam emitter is also added from the grid fluid menu. By default, the emitter's domain is unbounded and covers the entire fluid volume. This is exactly what we want in this simulation. Before we start to adjust the parameters, click on the grid fluid splashes group and change simulation to cache. The nodes turn yellow, and now the previously cached files will be used for the next simulation pass. Then remove the emitter from the global links panel and drag it to the grid fluid splashes and the grid fluid domain nodes. Finally, drag the emitter directly to the exclusive links panel. The interacting nodes are the rocks group and the K-volume daemon. Please keep in mind that foam does not need a gravity daemon because the foam particles will be automatically placed by the Hybrido solver. With gravity, the foam will accumulate in the wave troughs. Now we can go on with the settings. When you have a look at the particles panel, you can see that the particles type is set to dumb. You can of course choose a different type as well, but this will drastically increase simulation time and might falsify the results. The foam-specific parameters can be left untouched for the first simulation because the default setting is suitable for many cases. The only relevant parameter here is stringiness. If you can see the filaments or ripples with the foam particles, then you should decrease this value to suppress this effect. The number of foam particles can quickly become very high, especially with strong splashes and turbulent areas. A very good method to increase this is radius threshold, because splash particles with a radius smaller than the given threshold will not be able to create foam. The emitter's resolution parameter has only limited influence, but this can be changed as well. When you are satisfied with the results, you can create a playback to evaluate your simulation. To make the particle types distinguishable, it is a good idea to specify a colour, for example white for foam. To get a better impression of the mesh, it is possible to apply an OpenGL shader. Just open the Mesh's shader panel, select Transparent, and click on Environment Map to load an image. Images from skies are perfectly suited.